Hello, I'm Simon Cox. Welcome to this video which documents where proof by induction fails. I'm here at Pembroke Lodge in Richmond Park. The philosopher Bertrand Russell and his elder brother Frank were brought up here by his paternal grandparents, Earl and Countess Russell, after his mother died in 1874 and his father in 1876. Although an idyllic location, Bertrand didn't like life at the lodge, which was very strict and formal. This was due to his grandmother's Presbyterian upbringing. In 1890, Bertrand won a scholarship to study for the mathematical tripos at Trinity College, Cambridge. Well, enough about Bertrand. We're here to discuss proof by induction. So what is it? Proof by induction can be used where you have an infinite set of denumerable propositions, P1, P2, P3 and so on, that you wish to show are all true. There are two steps to the proof. The first is the initial or base case where you prove P of 1 is true. This is followed by the inductive step where you assume that proposition P of n is true and use this to show that P of n plus 1 is true. Using the initial base class, you can use the inductive step to show that as P1 is true, therefore P of 2 is true, and then you can use the inductive step again on P of 2 to show that P3 is true. This means you can count up to any number, showing that all the propositions are true. But let me play devil's advocate for a second. Let's assume that there are a set of untrue propositions. Now, as the propositions are numbered, we can order them, and there will be a least member. Say this is P of k. Now, P of k is the first untrue proposition. Therefore, the proposition before it, P of k minus 1, is true. But we can use the inductive step to show that P of k is true. This contradicts our initial assumption, and there are therefore no untrue propositions. To show proof by induction fails, we use a variant of the Ross-Littlewood paradox. It utilises two hoppers, one containing an infinite number of numbered red balls and the other a corresponding number of numbered blue balls. Below are two vases into which the balls will fall. The balls are moved to the vases in a sequence of steps. At each step, the next two lowest numbered balls are released from their hopper and moved to the vase below. Once they are in the vase, we move the lowest numbered red ball from the blue vase to the red vase, and the lowest numbered blue ball from the red vase to the blue vase. A supertask is used to control when each step occurs. A step occurs when half the remaining time till noon expires, the clock being initially set to 1 minute to noon. At 30 seconds to noon, step 1 occurs. The first two balls are released from each hopper and make their way to the vases. The lowest valued red ball in the blue vase is moved to the red vase, and the lowest numbered blue ball in the red vase is moved to the blue vase. At the end of this step, note each blue ball in the blue vase is paired with a red ball, and each red ball in the red vase is paired with a blue ball. When half the remaining time expires, step 2 occurs. The next two lowest valued balls are released. Again, the lowest valued red ball in the blue vase is moved to the red vase, and the lowest numbered blue ball in the red vase is moved to the blue vase. At 7.5 seconds to noon, step 3 occurs, and the next two lowest numbered balls are released. Again, we move the lowest valued ball to their corresponding vase. At 2 to the minus n minutes to noon, step n occurs, and we have the following position. Blue balls 1 through n are in the blue vase, each paired with a red ball, and the red vase contains red balls 1 through n, each paired with a blue ball. When half the remaining time to noon expires, step n+1 occurs, and the next two balls are released. Again, we move the lowest valued ball to their corresponding vase. By noon, a countably infinite number of balls have been released. We'll use proof by induction on the contents of each vase. But first we note the number of blue and red balls released are equal. Now consider the blue balls in the blue vase. Base case, we have blue ball 1. Induction step, we assume blue ball n is present. In the very next step, blue ball n+1 was moved to the blue vase. So blue ball n present implies blue ball n+1 is also present. Proof by induction shows all blue balls are in the blue vase and each is paired with a red ball. The fact that the number of blue balls released equals those of red leads us to the conclusion that all the balls are in the blue vase and the red vase is empty. Now let's look at the contents of the red vase and use proof by induction. Base case, we have red ball 1. Induction step, we assume red ball n is present. In the very next step, red ball n+1 was moved to the red vase. So red ball n present implies red ball n+1 is also present. Proof by induction shows all red balls are in the red vase and each is paired with a blue ball. The fact that the number of red balls released equals those of blue leads us to the conclusion that all the balls are in the red vase and the blue vase is empty. These two results contradict each other, therefore proof by induction fails. But what conclusion can we draw from this result? Well, it shows that infinite mathematical processes do not complete. And we can't, for example, consider the set of natural numbers as being a complete set. An example where completeness causes problems is Russell's paradox. He considers the set of sets that don't contain themselves. Now, if this set contained itself, then it can't be a member. But if it's not a member of the set, then it must be a member. This causes a contradiction, and it's all caused by assuming that the initial set was complete. I would have liked to have shared this result with Bertrand. I think it would have answered some of the questions that he had. This idea of completeness causes incorrect conclusions to be drawn in other areas of mathematics and mars our understanding of physics. In future videos, I'll be documenting some of these, so stay tuned. Oh, and if you're still here, thank you for watching.